Hello viewers, welcome to this module on overall revision of important topics of the classical linear regression model. In this module we will begin with the model, then briefly lay down the assumptions of the model, after which we will take up estimation using ordinary least squares method and move on to the properties of ordinary least squares method estimation, the results, and then we will look at the sampling distribution of the estimates, which will be followed by testing of hypothesis, and then we will move on to prediction. So, let us get started. We begin with the model, which is given as yi is equal to beta 1 plus beta 2 x2 I plus beta k x k I plus ui. Yi is the explained variable and the set of x's are the variables that explain y. For simplicity, we take the x's as non-stochastic and ui is the random disturbance term. I is the number of observation running from 1 to up to n. So, that is the structure of the classical linear regression model. Now, the assumptions of this model are: first, expectation of ui is 0. Second, variance of ui, which turns out to be expectation of ui square, is equal to sigma square, which means that the model shows homoscedasticity. Number 3, we have expectation ui uj is equal to 0 for all I not equal to j, which means that there is no serial correlation or no autocorrelation in the model. These are the 3 fundamental assumptions, plus we have expectation xi uj is equal to 0, which means that the explanatory variables x's are not correlated with the random disturbance term. Together with this, it is necessary to assume that the random disturbance terms follow a normal distribution. So, in that case, assumptions 1, 2, 3 are summed up as ui follows independent normal with mean 0 and variance sigma square. So, that in a nutshell is the set of main observations. Of course, we also have one more implicit observation, that is, there is no perfect collinearity between the set of regressors, that is called absence of perfect multicollinearity. So, any x, say x 2, cannot be a linear transformation of x 3. We cannot have any x as a linear transformation of any other x. So, this is called no perfect multicollinearity. So, given this model, we use the ordinary least square method of estimation. What we do is we minimize the sum of square of residuals of estimation. So, the OLS method of estimation is to minimize the sum of square of errors with respect to the beta variables, which are estimated as beta hats. So, what is EI? EI is the error of estimation. So, YI is estimated YI plus EI, and estimated YI is beta 1 hat plus beta 2 hat x2I plus beta k hat x ki. So, therefore, EI is equal to YI minus beta 1 hat minus beta 2 hat x2I minus beta k hat x ki. So, that is the error of estimation for the ith observation, and the square of that is expressed by putting a whole square and then we sum from 1 to n. So, that is the expression for the sum of square of errors, and we minimize EI square summation with respect to beta i's. This gives us the normal equations as first summation EI is equal to 0. You take the derivative with respect to beta 1 hat, it gives us summation EI equal to 0. Take the derivative with respect to beta 2 hat, that would give you summation EI x2I equal to 0. So on and so forth, you would get summation EI x ki is equal to 0. So, these are the normal equations. These are known as the normal equations from which we obtain the estimates beta 1 hat, beta 2 hat, beta k hat. So, if we solve all these normal equations simultaneously, we get the estimated vector beta 1 hat, beta 2 hat, beta k hat, which is called beta hat. This vector is known as beta hat. That is a vector beta hat. Now, if we have more than 3 variables, then it becomes unwieldy to use equations like that, which is why we often use matrices. So, in matrix form, it is convenient to write the normal equations as x prime E is equal to 0. What is this x? X is the matrix 1, x2 up to xk, x2 up to xk, and then again x2 up to xk. First observation, second observation, nth observation. So, when you write x prime E equal to 0, first column becomes first row and we get summation EI equal to 0. second column becomes second row and we get ei x2i summation equal to 0. Similarly, last column becomes last row and we get summation ei xki is equal to 0. Now, having written that, we can also arrive at the OLS estimates in matrix form. So, from here we write x prime, and instead of E we write y minus y hat is equal to 0, which means x prime y is equal to x prime y hat, which is equal to x prime x beta hat, which means beta hat is equal to x prime x inverse x prime y, and the model is given as y is equal to x beta plus u, so that y hat is equal to x beta hat. So, the ordinary least square estimates are given in matrix form as beta hat is equal to x prime x inverse x prime y, where this beta hat is exactly this vector. Now, it is easy to transform the model in deviation form. So, this beta hat can be written as beta 1 hat and b hat, where this b hat contains all other betas apart from beta 1, and naturally this is an estimate of beta which is beta 1 and b, and analogous to beta hat we get the estimate of the vector of the coefficients beta 2, beta 3, beta k estimated as b hat is equal to, just note the similarity, it will be the same expression but only in deviation terms. So, that is small x prime x inverse small x prime y. When we write small letters, these are in deviation form. So, let us look at the properties of the OLS estimates. As is evident, these are linear in yi's, and because yi is linear in ui's, so they are linear in ui's also. There are some important implications of the OLS estimates such that from the first normal equation what we get is the mean of y must be equal to the mean of estimated y, because the mean of the error is 0. So, y bar is equal to y hat bar. So, the mean of the observed values of y must be equal to the mean of the estimated values of y. And this happens only when there is an intercept which gives the first normal equation. As already mentioned, the betas are linear in yi's as well as linear in ui's, and what we get is that such estimates are the best linear unbiased estimates. They are the best linear unbiased estimates. That means among the linear unbiased estimates, these OLS estimates have minimum variance. Unbiasedness means expectation of beta hat is equal to x prime x inverse x prime expectation of y, and expectation of y is equal to x beta. So, this is equal to expectation of x prime x inverse x prime expectation of x beta plus u, while expectation of u is already equal to 0. So, therefore, we get x prime x inverse x prime x beta, which is nothing but beta. So, it is an unbiased estimate, it is linear, it's unbiased, and among the class of linear unbiased estimates, the variance is minimum. So, that is why we call it the best linear unbiased estimate. Now, from this step we will move on to the sampling distribution. We will move on to the sampling distribution of the estimated betas. So, we say that beta hat follows a normal with mean beta and variance sigma square x prime x inverse. Similarly, b hat follows a normal distribution with mean b and variance sigma square small x prime x inverse, where beta is equal to beta 1 and b is equal to beta 2 through beta k. So, these sampling distributions help us to carry out tests of hypothesis, and a simple demonstration of this sampling distribution is as follows. We know that beta hat is equal to x prime x inverse x prime y, which is equal to x prime x inverse x prime x beta plus u, which is equal to beta plus x prime x inverse x prime u. So, as I already mentioned, beta hat is linear in ui's and expectation of beta hat is beta. So, variance of beta hat is given as expectation of beta hat minus beta multiplied by its transpose, which is equal to x prime x inverse x prime expectation u prime x prime x inverse, and this is sigma square I. So, that we get variance as sigma square x prime x inverse. So, that is the variance of beta hat. Similarly, variance of b hat is sigma square small x prime x inverse, and because u, the disturbance vector, is following a normal distribution and beta hat is linear in u, therefore, beta hat also follows a normal distribution. So, for that example, let us take the model yi is equal to beta 1 plus beta 2 x 2I plus beta 3 x 3I plus ui. It is a 3 variable model. So, here x prime x will be given as summation x 2I square x 2I x 3I x 3I x 2I and x 3I square. So, therefore, the inverse of this is given as 1 upon x 2I square summation x 3I square summation minus x 2I x 3I whole square, which is nothing but the determinant, times the matrix x 3I square x 2I square minus x 2I x 3I and minus x 2I x3i. So that is the variance covariance matrix, and if you multiply this with sigma square, we get the variance covariance matrix. That is, variance of beta 2 is sigma square summation x3i square divided by this determinant. Variance of beta 2 is summation x3i square divided by this expression, all multiplied by sigma square. Summation variance of beta 3 hat is summation x2i square divided by this expression in the denominator times sigma square. So that gives us variance of beta 2 hat is equal to sigma square divided by summation x2i square, because here we had x3i square and here we have x2i square, x3i square into 1 minus r square 2 3. So this x3 and this x3 gets cancelled and we have sigma square divided by summation x2i square into 1 minus r square 2 3. Similarly, variance of beta 3 hat is given as sigma square divided by summation x3i square into 1 minus r square 2 3. As is clear, for beta 3 this is x3i but cleansed of the effect of x2. For beta 2 it is x2i but cleansed of the effect of x3. Now, naturally the question arises, how good is the fitted model, for which we introduce a concept called goodness of fit. This concept requires us to split the total sum of squares into explained sum of squares and residual sum of squares. So we know that y is equal to y hat plus e, and these are all vectors, plus we know that y bar is equal to y hat bar and e bar is equal to 0. These are scalars. So if we deduct the common y bar from each element of this capital Y vector, we get small y. Correspondingly, if we deduct y hat bar from each element of this column vector, we get small y hat, and since e bar is equal to 0, we can safely write plus e. So that is, the model as observed is equal to estimated plus error in deviation terms, and we define the total sum of squares as summation yi square I going from 1 to n, which is nothing but y prime y. So y prime y will be equal to y hat plus e prime times y hat plus e, which will be equal to y hat prime y hat plus twice y hat prime e plus e prime e. Now remember that y hat is equal to small x b hat, just because capital Y hat is x beta hat. So y hat prime e is b hat prime x prime e, and x prime e is equal to 0 by all the normal equations which we have already explained. So this term becomes equal to 0, and we have y hat prime y hat plus e prime e, which is written as total sum of squares is equal to explained sum of squares plus residual sum of squares. And obviously, anyone can guess that the higher the component of explained sum of squares, the better is the fit of the model. So, the goodness of fit of the model is explained by capital R square, which is explained sum of squares by residual sum of squares. What is this capital R square? It is the square of the multiple correlation between y on one hand and the entire set of variables x2, x3, x4. So, 2, 3 dot 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 up to k. So, that is a measure of the goodness of fit of the model. Now, one important thing about this is that normally as we go on increasing the number of regressors of the model, total sum of squares remains the same, but explained sum of squares tends to rise. So, one would be able to get a very high explained sum of squares by simply adding the number of explanatory variables, even if such variables are not always relevant. So, to put a check on that, there is a related concept called adjusted R square. We come to adjusted R square, but before that let us once again write the relation between TSS, ESS and RSS. So, TSS is equal to ESS plus RSS, and if we divide throughout by TSS, we get 1 is equal to ESS by TSS plus RSS by TSS. This by definition is equal to R square, and this therefore becomes 1 minus R square. So, as we were discussing, the adjusted R square is given as R bar square, again y on 2, 3 up to k is given as 1 minus RSS by TSS. Just note, till here it is 1 minus RSS by TSS, which is our familiar R square. 1 minus RSS by TSS is 1 minus R square. So, that is up to here we have R square. Now, how do we adjust it? We divide by the respective degrees of freedom. So, this has n minus k degrees of freedom, this has n minus 1 degrees of freedom. So, that is basically our adjusted R square, which means that if we add on more variables, explained sum of squares might go up, but there is a loss in the degrees of freedom. So, we sum up the result on TSS, ESS and RSS in this table as source. What is the source of variation in the model? We have the regression as one source, we have the error as another source, which make up the total. So, what are the sums of squares? This is explained sum of squares which comes from the regression, RSS which comes from the error, and the total is TSS. What are the degrees of freedom? Since we have k parameters beta 1 through beta k to estimate, so RSS has n minus k degrees of freedom, and here we have n minus 1, and the degrees of freedom of explained sum of squares is k minus 1. There are actually k minus 1 slopes, beta 2, beta 3 up to beta k. So, that shows the degrees of freedom, and finally, the mean square is known as the ratio of the sum of square divided by the corresponding degree of freedom. So, this is RSS by n minus k, and finally, what is the use of all this? We can find the F statistic for testing the overall goodness of fit of the model using ESS by k minus 1 divided by RSS by n minus k. Let us write this result clearly separately. So, ESS by k minus 1 whole thing divided by RSS by n minus k follows an F distribution with k minus 1 and n minus k degrees of freedom. Once we do the estimation and calculate the value of the F statistic, we will check and see whether F calculated exceeds F k minus 1 n minus k at the alpha percent level of significance. If the calculated F is greater than the critical value of F, this is called the critical value, then we reject the hypothesis that each of these betas is equal to 0. So, viewers, we have already started the topic of testing of hypothesis. The first test that we take up is test of overall goodness of fit, and that is formalized as the null hypothesis H naught, that is beta 2 equal to beta 3 equal to dot dot equal to beta k equal to 0, that is B is equal to 0 against H1 B is not equal to 0. So, under the null hypothesis, ESS by k minus 1 divided by RSS by n minus k follows F distribution with k minus 1 n minus k degrees of freedom, and if the calculated F calculated exceeds F critical, which is F critical? This value, that is, if you draw the F distribution, then that is the alpha percent area. So, this is F alpha with, of course, k minus 1 and n minus k degrees of freedom. So, if the calculated value of F falls in this critical region, then we reject the null hypothesis. So, we reject the null hypothesis if calculated F is greater than critical F, otherwise we accept it. So, naturally a high value of F means that the model is such that we cannot say that all the betas are zeros. So, that is the test of goodness of fit. Interesting thing to note is we can express this F statistic in terms of R square. So, from this line we can say if you divide numerator and denominator throughout by TSS, then we have R square by k minus 1 divided by 1 minus R square whole divided by n minus k, that follows F k minus 1 and n minus k degrees of freedom. Now, that was the test of overall goodness of fit. We might also have tests involving individual coefficients or joint tests. So, supposing we want to test just one coefficient, beta 2 is equal to 0 against H1 beta 2 not equal to 0. What we do is we draw on the sampling distribution which we have already explained. So, beta 2 hat follows a normal as we saw with mean beta 2 and sigma square divided by x2i square by 1 minus r square 2 3. Under the null hypothesis, this beta 2 is equal to 0. So, if the null hypothesis is true, then beta 2 hat divided by sigma square by summation x2i square into 1 minus r square 2 3 follows the square of a normal distribution. That means it follows a chi-square distribution with 1 degree of freedom. Remember, sigma square is unknown. Another important result is summation ei square by sigma square follows a chi-square with n minus k degrees of freedom. Recall the analysis of variance table where RSS had n minus k degrees of freedom. Residual sum of squares had n minus k degrees of freedom. So, if you take the ratio of this chi-square and that chi-square which are independent because we have partitioned the sum of squares into explained and residual sum of squares and x and e are uncorrelated. So, if you take the ratio of that, then you get summation ei square by sigma square divided by n minus k. So, this basically is a ratio of chi-square 1 and chi-square n minus k divided by n minus k, and that is, as we know, is an F distribution with 1 and n minus k degrees of freedom. And from basic statistical properties, the square root of this will follow a T distribution with n minus k degrees of freedom. But before that, you just note that these two sigma squares get cancelled, and this expression summation ei square by n minus k is nothing but the estimate of sigma square. So, we write beta 2 hat square divided by sigma square hat divided by this expression follows f. So, let us write that first and then we will move on to the T distribution. So, from this step we can write beta 2 hat square divided by sigma square hat divided by summation x2i square into 1 minus r square 2 3 follows f with 1 and n minus k degrees of freedom. So, what is this? This is beta 2 hat square divided by the estimated variance, and the square root of that is equal to beta 2 hat divided by standard error of beta 2 hat, which follows T with n minus k. So, that is the standard form. The square root of the estimated variance of beta 2 hat, the square root of the estimated variance of beta 2 hat, the square root of the estimated variance of beta 2 hat is called the standard error. So, please remember this form, which will be very useful while carrying out other tests of hypothesis as well. And we reject H naught if T calculated exceeds T critical. So, this is a standard diagram for the T distribution symmetric, and this is alpha by 2% area, this is also alpha by 2% area. So, if the absolute value of this t statistic exceeds this critical value, then we reject the H naught. What is H naught? H naught was beta 2 is equal to 0, and rejecting H naught means accepting H 1 beta 2 not equal to 0. Now, this format of the test statistic is very important, because if we remember this, it is easy for us to develop the test statistic for similar tests which might involve 2 or more coefficients. H naught beta 2 equal to beta 3, which means beta 2 minus beta 3 is equal to 0, against H 1 beta 2 minus beta 3 is not equal to 0. So, we come back to the format, that is beta 2 hat minus beta 3 hat divided by standard error of beta 2 hat minus beta 3 hat will follow t with n minus k degrees of freedom, or if it is a 3 variable model, this would be n minus 3 degrees of freedom. For a k variable model, it will be n minus k degrees of freedom. What is standard error of beta 2 hat minus beta 3 hat? It is the estimate of the variance of beta 2 hat minus beta 3 hat within the square root. So, square root of the estimate of the variance of beta 2 minus beta 3 hat. What is this variance of beta 2 hat minus beta 3 hat? In a 3 variable model, it is variance of beta 2 hat plus variance of beta 3 hat minus twice covariance between beta 2 hat and beta 3 hat. And from our earlier discussion, covariance between beta 2 hat and beta 3 hat, if you remember from the sigma square x prime x inverse matrix, the covariance will be sigma square minus x2i x3i divided by summation x2i square x3i square minus x2i x3i whole square. X prime x inverse matrix had 4 elements. This element over here was minus of x2i x3i summation, and all this was divided by the determinant. That determinant is x2i square x3i square summation minus x2i x3i whole square. So, what is the estimate of this? It is the estimate of variance beta 2 hat which we know, variance beta 3 hat which we know, minus twice covariance, that means plus twice this, and all along we should remember that sigma square hat is equal to ei square by n minus 3 in this case. In the more general case, it will be n minus k. Similarly, if it were instead of this, if we write beta 2 plus beta 3 equal to 0, then we just put a plus sign, plus sign, and this minus will remain, and we can use this same format. What is the decision rule? Reject H naught at the specified level of significance, which we took as alpha, if t calculated exceeds t critical. Similarly, we have one tail tests also. Now, before moving on to another part, it is very useful, instructive to note that in general all these tests can be expressed as H naught R beta equal to R and H1 R beta not equal to R, and this is called test of linear restrictions. These are the restrictions. We will test whether these restrictions are true or not. So, once again, very easy way of remembering is, if we allow these restrictions and estimate the model, then we get restricted residual sum of squares, whereas if we do not put these restrictions, then we get unrestricted residual sum of squares. The difference is restricted RSS minus unrestricted RSS. You divide this by number of restrictions Q. That means if R is a column vector with Q elements, then Q is the number of restrictions, and divide this whole thing by unrestricted residual sum of squares by n minus k. That follows F with Q and n minus k. So, that is the general format of carrying out tests of linear restrictions. In the 3 variable model, beta 2 hat is equal to summation yx2 x3 square, of course yi x2i x3i minus yi x3i x2i x3i all upon summation x2i square x3i square minus x2i x3i whole square. That follows from b hat equal to x prime x inverse x prime y. X prime x inverse matrix has already been discussed. X prime y is nothing but x2i yi and x3i yi. Now, this can also be written as, you see yx2 divide x2 square is nothing but beta y on x2, x3 gets cancelled, and this denominator, of course, we can take this and write as 1 minus r square, take it common. So, yx2 divide x2 is beta y2, x3 gets cancelled, minus yx3 divide x3 is beta y3, and x2 x3 divide x2 is beta 3 2, and in the denominator we have 1 minus r square 2 3. So, that is another important relation between beta 2 from the multiple linear regression model or classical linear regression model and simple regressions. Similarly, beta 3 hat would be, all these are beta hats, beta hat y3 minus beta hat y2 beta hat 2 3 divided by 1 minus r square 2 3. Similarly, the partial correlation between y and 2 given 3, the partial correlation between y and x2 given 3, that means the correlation between y purified of the effects of x3 and x2 purified of the effects of x3 is given as ry2 minus ry3 r32, and the denominator now you have 1 minus r square y3 1 minus r square 32, the square root of that. just note the similarity, beta y2, beta hat y2 r y2, beta hat y3, beta hat 32 r y3 r 32. Just differences here, you have 1 minus r square 2 3, but here you have just, here you also have 1 minus r square y3, the product of that and the square root of that. So, these are some other important relations between simple correlation coefficient and partial correlation coefficient. Another thing is that r square y dot 2 3 is equal to r square y2 plus 1 minus r square y2 times r square y3 dot 2. So, relation between multiple correlation, simple correlation, partial correlation, which can also be written as r square y3 plus 1 minus r square y3 times r square y2 dot 3. What is r y2 dot 3? It is the correlation between pure y, that means y cleansed of x3, and pure x2, that means x2 cleansed of x3. Now, having said all this, we come to the prediction of this model. We have the model y hat is equal to x beta hat, and we have some future value of x f. This is one row, that is x f is 1, x2, x3 up to x k, but f, that means future value, that is x f prime. We want to predict the value of y when x takes this value. So, that is obviously given as y hat f is equal to x f hat prime beta hat, and naturally expectation of y hat f is equal to x f prime expectation of beta hat, which is nothing but x f prime beta. So, the error is x f prime beta hat minus x f prime beta. So, therefore, we can write y f hat has an expectation of x f prime beta, which means y f hat minus expectation of y f hat divided by, again standard error. What is the standard error? Sigma square x f prime x inverse x f, but the square root of this, and sigma square is estimated, that follows a t distribution with n minus k degrees of freedom. So, the variance of this is now x f prime x inverse x f pre multiplied by sigma square, but estimate of that is sigma square hat, which is again RSS by n minus k, and the square root of that is nothing but the standard error of y f hat. So, this is what we use as the predictor, and we can express the confidence interval for the predicted value of y f. Before we end this module, I just want to mention two more things. One is, sometimes we do not have the beta 1 term, beta 1 is not there. So, that is called a regression through the origin. All procedures are the same, only thing is we do not have a model in deviation form. We no longer have a model in deviation form. So, TSS is equal to RSS plus ESS is expressed as y prime y is equal to y hat prime y hat plus E prime E. And remember, here E bar is no longer equal to 0, because we do not have the first normal equation. All other procedures are very similar, only thing is this model cannot be expressed in deviation form. Finally, whenever we run a regression, we have this yi is beta 1 plus dot 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 or beta 2 x 2I plus dot 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 beta k x k I, but these are measured in some units. So, sometimes for analytical purposes we want to make it free of units, which is why we standardize these variables. So, then we write yi star is equal to yi minus mean divided by standard deviation of y. Similarly, xi star is xi or x2i star is x2i minus x2 bar divided by standard, and once we do that regression on standardized variables, the result is important because the result now gives us unit free regression, which sometimes is very important for economic analysis. So, dear viewers, we come to the end of this module of overall revision. I have just selected some of the major concepts and topics of classical linear regression model, but remember that after all this the model needs to be tested for violations of the assumptions of the simple linear regression model, namely for heteroscedasticity, autocorrelation, multicollinearity. Only when that is done, we take the classical regression model, classical linear regression model as a satisfactory estimate of the real world phenomenon that we are trying to investigate.